All right, so in this video, we're going to use this Excel file that I've given you that has a flat track, elastic track, the flat ball force, and elastic ball force. If we plot this over time, let's see what we get. We got so we have the y position of the ball being tracked in a video over time, right? In this case, it's 9 seconds long, and we have the ball going from about what is this, 0.24 all the way up to 2 something meters, right? It keeps going up and down. All right, so this is not the person's hand being tracked. This is the ball being tracked. We also have yes or no if the person is in contact or the ground is in contact, right? So if we look at this, the person is in contact for these periods, and the ground is in contact for these small little snippets of time, right? Okay, so in the question 1, we want to find the force in the z direction, where z is a long gravity, acting on the ball versus total displacement. All right, so let's see. In this case, total displacement for us, we're going to look at the y displacement. X doesn't really matter. The ball doesn't really change much in the x direction. But in y, now we have these effects of gravity and things like that we need to take into account to talk about the amount of force acting on this ball over time. So let's say delta z, or delta y, whatever. That's going to be does this minus the previous frame, and we'll double click that to auto populate all of the rest of the data here. The total delta y is just going to be we're going to say this is the absolute equals this right here, and then on the second one we're going to go equals this plus the one above it, right? The J5. Okay. And we're going to make this thing the absolute value of the difference in displacement, right? Okay. So now over time, this ball just keeps displacing, right? We have basically total distance traveled, doesn't matter about the direction, okay? We also want to get the velocity of the ball. Say velocity. Okay, so that thing is going to be, this equals the y position, basically the same finite difference theorem, right? Y position at 2 minus y position at 1 divided by time at 2 minus time at 1. Okay, take a look at that thing. Yeah, that looks like a velocity. It goes pretty high velocity when we come down and slam the ball, and then it stops, it goes to 0, gets picked up, slam, slam, slam. Cool. That looks about right. And I want to talk about a delta time. So we'll talk about this as d delta time. This equals just this one minus this one. So time now minus time point before. Do that for all cases, and we get this thing's a constant, right? All this data was measured at a constant frame rate, so that's no surprise, right? Now we have a formula for change in momentum, right? If you look at the formula for change in momentum, that's dp, and this says this is the change in velocity times the mass of the ball. We want to make sure that the mass of the ball is money sign B, money sign 1, right? Thing locks that in place, and we'll go ahead and make that just double click that thing out so that we get change momentum throughout time. Let's go plot that thing. All right, this thing looks crazy, right? This is a lot of peaks here, but it also kind of makes sense, right? All these locations where we have very high change momentum, those are where the ball is contacting the ground. Okay, so if we want to look at the force the ball experiences, what we can do is take the change in momentum divided by the change in time, right? Because F dt is equal to dp. So here's the force. All that did was shift the units basically by dp, right? So, or dt. Okay, so next we'll do force due to ground, and we'll do force due to person. So this is whatever force we got times this this number 0 or 1, depending on if the ball is in contact with the ground or not, right? And similarly with the force due to the person, we'll just multiply this force times if the person is in contact or not. Oops. Okay, let's plot that. All right, that looks reasonable. Now we have two more forces. One is the force of gravity. So this thing's always acting on the ball. That's just the ball's weight times 10. Then we have, well, we got sum of forces. That's this plus that plus that. All right, so now let's look at the plots. So this thing is force due to ground. And I asked for that to be green. Come over, make that thing green. Cool. This one, we'll make this one force due to person. And but look at this, you know, this axis isn't so good, right? It's very noisy up here. Let's see if we can clean that up just by coming over and getting our axis marks. Let's go to like 1,000. Looks better. Let's go down more. Let's go to like 500. Okay. That looks reasonable. Actually, this is good data. Everything else was kind of just noisy. And we want to make this one red. Okay, so this one be force due to gravity, which is a constant number. Blue. Cool. And then sum of forces, we're going to make this one black. And let's go and take that, like, this axis down. Let's go to, like, 500 again. All right, let's go to 1,000, maybe. And no line. So we need to plot this versus, not time, but total displacement, right? So instead of time over here, we'll just do this, move this over to total displacement. All right, so this is the 4 plots that we need to do question 1, part A, right? So do the same thing for the elastic tracking, and you can just copy and paste these plots onto, let's actually make this down, maybe more like 1,000. See what that looks like. Yeah, that's more reasonable. Okay, so make sure your axes make sense here. Your axes, and go ahead and throw these plots down on your report. Sound good? All right.